Okay, so today we're going to be talking about inscribed angles and inscribed polygons. So the other angle we've talked about in a circle is the central angle. So central angle has the vertex that is in the very center of the circle. An inscribed angle has this vertex on the circle. So an inscribed angle has the vertex on the circle, and its sides are chords. Okay, so that part of the definition is there to stop you from having, like, if you have a vertex on the angle or on the circle like this, okay, and then you had just an angle that went off like that. That's not an inscribed angle. So the inscribed angle basically goes inside the circle like this, and so that angle intercepts a arc. Okay, so the measure of a central angle we talked about previously is equal to the measure of the intercepted arc. For inscribed angles, it's another easy one to memorize. The measure of an inscribed angle is half the measure of the intercepted arc. Okay, so what does that mean for down here? That means, hey, if I have RS as my arc of 48 degrees, this angle T, okay, is half the measure of the intercepted arc. So if the intercepted arc here is 48, half of that is 24. So this is a 24-degree angle. Now QR is this arc. If you notice, there's not an inscribed angle going to QR, okay? But the inscribed angle we have up here is this 50-degree angle at R, okay, QRT. So the measure of the inscribed angle is half the measure of the arc. So that means that this arc here of QT is 100 degrees. So I have this 100-degree, 50-degree comparison there. And because this is circle P, that means that this is a diameter. And as we know, a diameter cuts the circle in half. So you have two semicircles. So because these are semicircles, okay, a full circle is 360 degrees. So a semicircle is 180. Okay, so if this little piece here is 100, then QR is going to be the remainder of that 180. So this is going to be an 80-degree arc. All right, so we can do the same thing down here. Let's see if I need some more colors for this. Let's find the measure of arc SR. Okay, so SR, okay, is being cut out by this 31-degree angle like that in red. So the measure of the angle, okay, the inscribed angle is half the measure of the arc. So that means that this arc here is 62 degrees. Okay, so this is the measure of arc RS. And then for the measure of the angle STR, okay, so STR is this angle here, okay, so the measure of an inscribed angle is half the measure of the intercepted arc. So you got to kind of trace out the chords, and you'll see that ST and TR are the sides of this angle. So this angle T is half the measure of the intercepted arc. The intercepted arc is SR, so half of 62 is 31. Okay, and then do you notice anything about the angles? Well, this angle up here is 31. This angle down here is also 31. Huh. These angles are congruent. So STR is congruent to RUS. Okay, because they're both inscribed angles. Okay, and they both cut out this 62-degree arc. And so the measure of an inscribed angle is half the measure of the arc. So it apparently doesn't actually matter where this is, okay? If the measure of an inscribed angle is half the measure of the intercepted arc, then as long as it intercepts arc SR, it's going to have the same measurement. So it actually doesn't matter where this vertex goes. So you can almost imagine like dragging this vertex around the circle, and it actually will not change what that angle is. So that is one of the theorems for today. Okay. So if two inscribed angles intercept the same arc, they are congruent. Okay, so here you have angle D is cutting out arc AB, and angle C is cutting out arc AB. Therefore, angle C and angle D are going to be congruent. All right. My plan of making these shorter and faster is working so far. Let's see if we can finish this up. All right, so the measure of angle G, right? The measure of an angle, inscribed angle, half the measure of the intercepted arc. So this is going to be half of 90, so that's 45 degrees. So going the other way, if the angle is half the measure of the measure of the arc is double the angle. So that's 2 times 30, that's going to be 76 degrees. And then here, measure of angle X. Measure of angle X is half the measure of ZW. Okay, ZW is that arc that it cuts out. Angle Y up here intercepts the same arc, so they're going to be congruent by that theorem we just discussed. Okay, that theorem just saves you a little baby step, because if you did this the long way, this inscribed angle 72, that means that this arc is 144. It's going to be double that, and then this angle is going to be half of that. So the thing just saves you a quick minute. Okay, so inscribed polygons. Okay, so an inscribed polygon is just a polygon with all its vertices on a circle. Okay, so there's two kind of words here. There's inscribed, so you can take a shape, you can inscribe it in a circle. So inscribed, right, inside the circle. Or you can start with a shape. So if I started with, say, that triangle, okay, then if you were to create the circle, that's called a circumscribed circle. So the shape is inscribed, the circle is circumscribed. Okay, so this is an inscribed triangle. This is an inscribed quadrilateral. You can do that with pretty much anything. Okay, you can do that with any other shape. So a couple theorems here. So a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. And then conversely, if one side of the inscribed triangle is a diameter, then the triangle must be a right triangle. Okay, that's a very, very useful theorem, okay, that actually isn't anything new, because we already know that the measure of an inscribed angle is half the measure of the intercepted arc. So if you have a diameter, okay, then it cuts it into semicircles, which are arcs of 180 degrees. So the angle that does that cutting into that arc will always be less than 180, which means it'll always be a right angle. Okay, so when you're doing like constructions or something, if you have the diameter of a circle, you can literally draw the vertex anywhere on the circle, and it will be 90 degrees. Okay, that's a way of guaranteeing that you will get a right triangle. All right, now the second theorem, this one is not obvious, and I like to prove this one because I think it's so interesting. And that is that the only quadrilateral that you can inscribe in a circle is one where the opposite angles are supplementary. So we know that all four angles here add up to 180. Or excuse me, all four angles add up to 360. Okay? But the only way that you can get a quadrilateral to fit inside of a circle is if the opposite angles add up to 180. Okay? Actually, before I talk about that, let me just mention how, because we're talking about how this is the only quadrilateral that works. For triangles, they always work. Okay, so you always inscribe. You can always inscribe a triangle. Okay, because this, okay, is going to be half the measure of this one up here. This angle is going to be half the measure of this, and this angle is going to be half the measure of that, okay? So when you draw a triangle, okay, it'll always be the case that the opposite, each vertex of the triangle, okay, is essentially a different potential central angle, or inscribed angle. And because these three angles will always add up to 180, okay, this being doubled of this angle, this being the double of this angle, and this being the double of that angle, will always add up to 360. So that will always create a circle for you. Okay, so every single triangle, no matter how weird it looks, you can draw a circle that circumscribes it. That's not the case with quadrilaterals. Only special quadrilaterals can be inscribed. And so the reason for that, if we look at just, say, two of them, if I look at, say, angle D, okay, so the measure of angle EDG is half the measure of arc EFG, right? So you have this arc, EFG, being cut out by D. So the angle opposite D in this case is angle F. Okay, I'll just make this argument once, but it's the same argument with the other pair. So the measure of angle EFG is half the measure of arc EDG. So this arc going this way. Okay. So if you notice now, the orange arc that's opposite angle F and the purple arc that's opposite angle D make up the full circle. Okay. So what that means is that if I were to add these angles, okay, I'm going to drop the three-letter name because I really don't have space for that. So if I add angle D and angle F, okay, so if I'm adding these two things, I'm adding these two. If I factor out the 1/2, that's the measure of arc EFG and arc EDG. Okay, and because these two arcs make up a full circle, this is 360 degrees. And so half of that is 180. So no matter what you have here, as long as this is inscribed inside of a circle, the opposite angles are going to be supplementary to one another. Okay. So you can answer those questions in two ways. Here's one type of question where I just give you the inscribed quadrilateral, and then you got to solve for some stuff. So in this case, I know that these are inscribed, so the opposite angles are supplementary. So that means that y plus 75 is 180. So in this case, y is 105. And then 80 plus x are supplementary. So x is going to be 100. Okay, and then with part B here, the opposite angles here are 4b and 2b. So 2b plus 4b is supplementary. And then 2a and 2a are supplementary. So this is 6b equals 180. So b equals 30. This is 4a equals 180. So a equals 45. Okay. So that's one type of question. Another type of question could just be the question, can you circumscribe a circle around a given quadrilateral? And then that's a yes or no question, where to answer that, you're just looking at the opposite angles and seeing, are the opposite angles supplementary? If they are, the answer to the question is yes, you can circumscribe a circle around them. If the opposite angles are not supplementary, then the answer is no, you cannot. Okay? All right. Good luck. Email me with any questions. Take care.